Hey everyone, so I wanted to talk about the last thing dealing with conservation momentum. It's called center of mass. Now, for the most part, this is actually a subject that we're going to touch in much more detail in the rotation unit. It's going to play a lot bigger of a role there, but I'm going to briefly mention and describe what center of mass is, show you kind of like a way to kind of eyeball where the center mass will be, and then I'll talk about how that relates to this idea of conservation momentum. So, for the most part, you may notice that whenever we've been talking about these problems and doing all these calculations, we've pretty much always ignored the size and shape and dimensions of the objects. That way, we never really worried about whether or not the object was a sphere, a block, how long it was, how big it was. We just cared about its mass, and that was it. And in fact, when we did the orbiting questions, where we had, or the gravitational force questions, where we had objects separated by a distance, I specifically mentioned this that for the most part, we're going to ignore the size of the object, and all we really care about is the mass and how far away you are from the center. And that for the most part, we are essentially boiling down these giant planets and stars to just little points in space that contain all of its mass. So what we were essentially doing is we were only really considering the center of mass of the object. And everything that we've done so far, all the laws of physics, all the different kinematics equations, all these relationships were really based off of the center of mass, because it turns out that we can do this for all objects. That regardless of how complex or irregularly shaped the object is, it has a center of mass, which is essentially the average point in space along the object where it contains all of its matter. So when we talk about Newton's laws and the forces acting on the object, we're talking about the forces acting at the center of mass and on the center of mass and how that's affected. This leads into some really unique scenarios that we'll talk about in a second. Another way to think about the center of mass, the easiest way, is that it's pretty much the location where if you placed it on some sort of balance, on some sort of fulcrum or pivot point, that's going to be a point where it's going to balance on. It's the balancing point because by definition, it is the average location of the matter. So you have just as much matter on one side as there is on another. So that's the idea about the center of mass. So if you can figure out where the point of balance is, you'll know where the center of mass roughly is. Now, we're not, like I said, we're not going to figure out the calculation wise where the center of mass is. Instead, there are some simple things that we could do to kind of estimate where it's going to be. For example, one thing to note is that objects that have uniform mass or uniform density, that's like a phrase that they like to say a lot. Those are key phrases that they use to say that the center of mass is directed straight in the middle of the object. So, for example, a ruler is something that is typically of uniform mass intensity. So, if I wanted to know where the center of mass was, it would be directed right in the middle of the ruler. If we had a triangle, it would be right in the middle of the triangle. And for something like a ball, again, right in the middle of the ball. So we could do the same thing for a system of masses. So try this out. We have two people of equal mass. So pause video, work itself. We'll go in a second. All right. This one shouldn't have taken too much effort. Again, since we have two objects of equal mass, then just like with the uniform mass density, ruler scenario, we would want to we would say that the center mass is right at C. And like I said, we can think of the center mass as being the location of balance. If you consider putting these two people on on one of those balance beams, one of those seesaws, if the seesaw's fulcrum pivot point is directed right at C, right in the middle, then you'll end up having the beam completely balanced because both people are equally massed. Now, what if the object isn't isn't uniform, and it's more like an irregular shaped object? Well, one of the easy ways to do it, if we had the object physically on hand, is we could actually hang it at various locations along the object and draw lines going straight down. And what we would find is that the point where all the lines cross is going to be crossing along the center of gravity, the center of mass. Now, the reason this works is essentially because of the fact that gravity acts vertically straight down, and the force of gravity actually acts roughly where the center of mass is. Again, you know, relatively speaking. So when we draw these lines going straight down, these lines are passing along the force of gravity every single time. Sorry, the center of mass because of the force of gravity. So wherever they cross all together is going to be that shared point in space where all the mass is going to be located. Now, there are ways to find the center of mass for irregular shaped objects that are still somewhat more simplistic. So, for example, let's say we have a broom that has a uniform handle and then it has like an extra mass on the end, and we want to know where the center of mass would be. Well, what we could do is treat this as two separate objects. This broom tip has a center mass right in the middle, we'll say, and this broom handle has center mass right in the middle of it, so right about here. So what I could say is, if I want to eyeball it, there's a mass here and a mass here. The center mass should be somewhere in the middle. According to this picture, it's right here, so that would probably imply that this is a little bit heavier. But for a lot of multiple choice questions where you have to try to figure out and estimate where the center of mass is, you would just have to get roughly around the location for it to be count points. Just like with the question that we just had, you would have a point here, 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 and here. So even though the center mass is actually a little bit closer to uh, E than it is C, D is still roughly where it should be, where the center mass might be. So this is kind of how you would do center mass for these types of objects. You basically split into two separate objects or whatever, however many objects you can, and just find the average location between those points that you make. So let's try the same thing with two different sized masses. So pause video, works up, and we'll go in a second. All right. So again, normally in the balanced case, the center of mass would have been over by C, but because we have the right side being a little bit heavier, it's going to shift the balance over to the next point, D. The reason why it's not going to be E in this case is because even though it doesn't explicitly say it, um, E is located actually pretty much right where the person is. In order for the center of mass to be shifted that far over, the person would have to be significantly bigger than the other person. In fact, it would have to be make it so that this person's mass was almost negligible. That way, it only shifted the center mass a little bit away from the main person. So the fact that this person is still like almost half the size as him, D is definitely a much better point to consider the center mass to be. Like I said, this actually, if we bring it back to the whole idea about planetary motion, if you recall, the equation that we used for planets orbiting around stars or any sort of orbit question, we had the force of gravity being set equal to the centripetal force. And one of the things I said is, in the cases where we're not dealing with a binary star system, but when we're dealing with like a planet orbiting a sun or a satellite orbiting the Earth, that these two R's were the same value because we assumed that the distance to the center of the object was the same as the to the center of the circle that it orbits. But it actually turns out that for planets and stars, the center of mass actually isn't directly in the middle of the star. It's a little bit shifted over. Um, so
in I think in our case it's I can't remember exactly where it is, but it is shifted from the center of our sun, and that what that also means is that this star actually wobbles a bit in its orbit, so it's not actually stationary. It too moves around in a circular motion. So took if we looked at the solar system from an outside view, we would actually notice the sun kind of going in a little bit of a wobbly motion as all the planets orbit around it. Like I said, we're gonna continue this idea about center of mass and how to calculate and how to deal with it a little bit more in the rotations unit. But what we're gonna do now is try to relate it back to what we've been talking about, which is conservation momentum. So one of the other things I mentioned was the fact that Newton's laws apply to the center of mass. So that means when Newton's first law said that an object in motion tends to stay in motion unless acted upon by an outside force, it turns out that we could actually rephrase that to say the object or system's center of mass will remain at rest unless acted upon by an outside force, and that an object or system's center of mass in motion will remain in motion unless acted upon by an outside force. So we're just taking the first law statement and altering it to what it actually is entailing, which is the center of mass is what we're actually focusing on. This can be very easily seen with irregularly shaped objects. So if you had something like a wrench or a bat or something that was kind of uh, unbalanced, where one side might be heavier than another, and you try to toss it into the air, like a projectile, you might notice that it kind of makes a weird arc. That the arc is a little bit more chaotic than we would expect, and you might think that could be caused by air friction, and that the equations that we have aren't really suitable for it. But it turns out that if you actually record the object being thrown in the air and track the location of the center of mass, while the object spins around in this chaotic fashion, the center of mass will still follow the typical parabolic pathway that we would expect for a projectile. You can find a lot of videos on YouTube with this. I probably will put this in later on, but it is pretty interesting to have the center of mass located and see that it does follow the arc despite the bad or the irregularly shaped object kind of flailing around awkwardly. Um, so the laws of physics pertain to the center of mass. And it doesn't matter whether it's the center mass of an object or of a system, it's the same thing. So, what else can we talk about with center of mass? Um, Now, one thing that this leads into, and this is starting to get into this conservation momentum aspect. Let's say that you're standing on a platform, and this platform is free to move. So, for example, one of those flatbeds that you see at Home Depot or at Costco or BJ's or something. If you've ever stood on one and then tried to walk on the other side, you'll probably notice that the flatbed moves in the opposite direction. Now, we could explain this motion in terms of forces that as you move forward, you push your foot back, and that pushes the flatbed backwards, because of Newton's third law, equal and opposite forces. Well, we could also use this dealing with conservation momentum, and it actually turns out that the way the object moves actually relates to this idea of center of mass. So, what this means is that when the object moves back, it's doing this in such a way so that the center of mass doesn't change its motion. So, this is just more of a visual scenario that let's say we have a person in a canoe, the canoe is on the water, the canoe's center of mass is right here, and the person is located over here. So the center of mass will be somewhere in between the person and the center of the canoe. So in this case, it's right here. When the person moves to the other side, there are no outside forces acting on the system. And as Newton's first law says, if an object's at rest, it will stay at rest unless acted upon by an outside force. When this person walks to the other side, he is providing what we would call an inside force, an interactive force between the two objects. So while they move outside the entire system, there is no outside force. There's no friction. There's nothing like that. So when he moves to the right, the canoe moves to the left in such a way that this center of mass does not change its motion. Because there's no outside force, there shouldn't be a change in the motion of that center of mass. So we can actually do calculations with this and figure out basically how far the platform moves. The person walked a distance of L, but it actually only resulted in the canoe moving a distance of L divided by 5. So, you know, why is that? It all pertains to this idea about center of mass. We can actually take it one step further. Like I said, we can use conservation of momentum to actually figure out how fast the platform goes based off of this idea that because there's no outside forces, that the center of mass has to stay the same, that the objects, the momentums of the two objects should be equal. So what about if the object is moving? Well, again, the center of mass will still keep doing what it's doing. So in this case, if the canoe was actually going down the river, let's say, and you and the canoe were initially, I would say you weren't moving on the canoe, but you guys were moving down the river at a constant speed of 5 meters per second, the center of mass is moving along with you with that same speed. If you start moving to the front of the canoe, once again, the canoe is going to move backwards. So now both of you will have different speeds, but the center of mass will still be moving with the exact same speed as before because there's no change in the outside force acting on you. All right. So here's a scenario that we have two carts moving towards each other, and it says that the center of mass is moving to the right at 5 meters per second, um, and then we would say that even after the two objects collide, their final speeds are going to be drastically different. They could both be moving to the right. Maybe one moves to the right, the other one moves to the left. We don't really know what's going on, but as long as there's no outside forces, then the center of mass will still continue moving to the right at 5 meters per second. And again, that's because of the fact that even though they do apply a force on each other, that force is considered inside the system. And what we really care about are the forces that are outside the system. All right, so let's practice a question. So pause the video, works off, and we'll go over in a second. All right. Part A says, what's the direction of the motion in the center of mass? So here we have we have these two carts, one that is free to move and the other one that's not free to move essentially. And we want to know what is the direction of the center of mass once one object starts moving after the spring releases and the other one stays still. Well, because one of the objects is moving to the left and the other object is motionless, that tells me that the direction of center mass should be to the left because they are starting to get further apart. So the center mass is going to drift towards the middle of the two objects essentially. And because that middle is changing, it's going to be going to the left. Now for part B, if we think about it, in the beginning, neither cart was moving, so the center of mass should have been 0. If the center of mass starts moving to the left, that means there has to be an outside force that's affecting the center of mass. So what is it? Well, it's the fact that the block that's made of wood without wheels is not free to move. So something is keeping that block from moving freely, and that something is friction. Again, for the most part, the outside force that we're usually referring to is going to be friction. Or maybe there's someone physically holding it in place and preventing it from moving. But whatever it is, that's what we're usually referring to as an outside force. Now, so far we've just talked about, conceptually what direction the center mass would go. Well, again, how can I find the speed of the center mass? Is it possible? Well, yes. What we can do is use the sticking equation. It turns out that if we consider a scenario that two cars collide and stick together, when they move as one object, that's essentially the motion of the center of mass. Like if they stick together and move together as one, then their center of mass is going to be moving with that same exact velocity. And because momentum's conserved, that means the momentum it had before they collided and stuck together uh, is equal to that, and that the center of mass should also have been moving with that same speed because there's no outside forces. So the center of mass will keep doing what it's doing. Um, so this actually works for every single collision, even the ones where they either don't stick or don't even collide. So you can have two cars that are moving in completely opposite directions, never ever colliding, and you can still talk about the center of mass as if they did collide. So it's a really interesting thing that this sticking equation does get reused for finding the speed of the center of mass. All right, so here's the first question. Pause the video, work self, and we'll go over a second. All right, so here we have two balls rolling towards each other in a head-on collision. So they will actually collide, um, and they do end up bouncing off. But again, since they want the speed of the center of mass, I don't really care about their final speeds. I don't care about what happens after they collide. So what I'm going to do is I'm going to do conservation of momentum. I'm going to take the momentum of the two objects. I have to make sure that I make the second velocity negative because they're moving towards each other. So one's going to be moving to the right, the other one's moving to the left. Different directions means different signs. So I plug in my numbers and I get that the final speed is going to be about 2.3 meters per second. So the center of mass after they collide is going to be moving 2.3 meters per second in the same direction as the red ball, since that ball was the one I made positive. All right, and here's 19. So pause video, works up. Let me go in a second. All right, so this should be the last one. So here we have, we're actually going back to the previous question, not question 18, but question 17. So it's the same scenario. I worded it a little bit different, and I mentioned that you want to make sure that you assume that they have equal masses. So again, if I want to calculate the speed of the center mass after the collision, so I could do the sticking equation, and what I would do is do conservation momentum, take my values. The car with the wheels moves with the speed of 5. The one without wheels doesn't move at all, so it's just going to be 5m plus 0m. And then again, we're going to consider that they stick together, even though they're moving in opposite directions. So I get 2mv on the right-hand side. Solving for v, I get that's 2.5 meters per second. So because the one car is moving with the speed of 5 meters per second, the center of mass's speed is actually going to be drifting to the left with it at pretty much half the speed. For part B, it wants to know what the speed of the center mass was before the collision. Well, you could say, well, maybe the speed of the center mass should be the same, 2.5, because that's why I said that Newton's laws are saying that they should be the same before and after. But if you remember, the key phrase there was that the center of mass will keep doing what it's doing in the absence of an outside force. And as I said before, this cart does have an outside force. So we would actually kind of have to recalculate it. But here's the nice thing. When I recalculate it using the initial values, well, the spring cart is starting at rest, and the block without the wheels starts at rest. So on the left-hand side, it would just be 0. Therefore, on the right-hand side, the v would have to be 0. So the center of mass actually before the collision was 0, and after the collision, it shifted over at 2.5 meters per second due to this presence of friction. All right, so that was essentially it. This is kind of the idea about center of masses that you have to know. There are a few practice problems that you'll see dealing with this. It is definitely important that you kind of keep an eye out for it because it does pertain with the whole idea of conservation momentum. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.